Hello. Hello, guys. So, in today's tutorials, okay. I'd like to thank you so much, all those who have sent their questions during the week. And in this tutorial of today, we are going to be looking at all those questions which you have sent, and we'll equally be looking at some past questions as well that are going to help us in the course of this Sunday's revision. And take notes, guys, that we have revision on Sundays at 2 p.m. for the various topics we have covered during the week. So we'll start by looking at the first question that we have here. So first of all, I would like to make comments here that our hearts, we are not really happy because many people watch all of these videos, but people hardly subscribe. There are thousands of you watching these videos, but you have not sat down or think of subscribing, which is very, very important. And because of this, the hearts of our panelists are broken, as you can see, and they say they can't believe that you're watching this video and you have not yet subscribed. So please subscribe to motivate us and to do more. All right, we have somebody who is in class online now. Hello, happy Sunday. Yes, who is online? Adelaide? Is it Adelaide?
No, says Lina.
All right, Lina, happy Sunday.
Same person.
Yeah, it's been long since we have been having issues with connections, blackouts, electricity. In fact, all of those things, you know now. Let me not be mentioning them.
Yes, sir.
Yeah, so Lina, have you subscribed to this channel?
Mm.
You have not.
Yes, sir.
All right. Have you shared this block with your friends and different
Not
WhatsApp
yet.
groups?
Yes, I forwarded a message.
Okay, so today we are looking at tutorials on limits, and we will look at some of the questions that came in during the week. Did you send any question?
No, sir.
Okay, so let's start with this first question. You can see it, right?
Yes, sir.
Can you see your screen?
Yes, sir, I can see it.
Yeah, so with this first limit, we have about 50 questions to answer. So looking at this limit as x tends to 2, normally this is a polynomial function, right? So since a polynomial function, we can just take this limit directly, as you can see. So we can just move directly by substituting the values as x tends to 2. And this will give us 8 minus 3 into 2 plus 12 into 2 squared. That is 12 into 4. That gives us the limit to be equal to 50, right? Yes, Rodrigue. Good afternoon. Rodrigue. Alright, the second question is this. We have 6 plus 4t on over t squared plus 1 as x tends to minus 3, right?
Good
Yes,
afternoon, sir.
yes, good afternoon, Rodrigue. Welcome. How's your Sunday?
Yes, good afternoon, sir.
Alright, thank you. So for this particular limit, we see that if we put in the value of minus 3 directly, the limit exists and this limit is defined. So we just substitute, and this is what we obtain for the limit of this function as x tends to minus 3.
Yes.
Yes, are we fast?
Yes, sir.
If we are fast, you comment now. You are live. The whole world is watching. Okay. The third limit here, we have this limit as x tends to minus 5. With this limit, if I substitute minus 5 here, this is the result that we are going to have. So let us substitute minus 5 and see what we have. For the numerator, what does it give us? Minus 5 squared is 25 minus 25. So the
Right.
numerator will give us 0, right?
Yes, sir.
For the denominator, we'll have minus 5 squared, which is 25, plus 2 times minus 5, so 25 minus 10, which is 15, minus 15, 0. The numerator also, the denominator also gives us 0. So the limit here gives us 0 over 0. What is 0 divided by 0?
Say 0.
0 divided by 0 is undefined. It's not 0. So this limit is not defined. This limit does not exist. But the truth is that this procedure I have used is wrong. That is what I wanted to emphasize here. So what we can do here is to follow the algebra trick in which we identify that the numerator is a difference of 2 squares, which can be written as x minus 5 into x plus 5. And for the denominator, we equally see that the denominator can be factorized as a quadratic, which can be factorized to obtain x minus 3 into x plus 5, such that these two can cancel out, and we'll be left with x minus 5 on x minus 3. If we now substitute the value of x equals minus 5 here, we will have minus 5 minus 5, which is minus 10, and minus 5 minus 3, which is minus 8 now. That gives us minus 8. And minus 10 divided by minus 8 will give us 5 on 4. This algebra trick is very, very common in advanced level. So take note of this. Are we together?
Yes, sir.
Yeah. Hello, Rodrigue. All right. It seems he's having a bit of trouble. Now, to evaluate this limit as x tends to 8, if we look at this very well, we'll see that here we have the denominator will give us 0, right? Which will make the limit to be some sort of undefined, and the numerator as well. Numerator also give us 0. But if we factorize the numerator, this is the quadratic that we are going to have. Now over the denominator, which is 8 minus z. But if you look at the signs that we have here, this denominator is 8 minus z, while the numerator is z minus 8. So we have to do some sort of adjusting or balancing in the denominator so that we can cancel out. So we can equally write the denominator as minus into z minus 8. We have not changed anything. And from this point now, we can actually cancel out. These two can now cancel out after this adjustment. And we'll be left with the limit as z tends to 8 of 2z minus 1 over minus 1. When we put in these values, it will give us minus 15. Are we together?
Yes, sir.
If anything is not okay, you will have to tell us, okay? Yeah, if anything is not okay, it's good that we inform. Okay. Now let's look at the next limit. We are looking at the limit of this function if it exists. So normally with this function, we follow the same algebra trick that we have just seen. Factorize numerator, factorize denominator, cancel out. And these are the results that we are going to have. You have the limits to be equal to 2 on 5. So you can look at that very well. The limit will still give us 2 on 5.
So I have a question.
Yes.
So what if the numerator is a polynomial? Like the degree is 3 or 4. What are we going to do?
If the degree is 3 or 4,
Yeah, the degree of the numerator.
yes, in that case, we are going to look at factorization of polynomials. In which case, we have to use testing. For example, you test and say that what if x equals 1 is a root, or x equals 2 is a root, x equals minus 1 is a root. You test, like we did in the topic on chapter 4, which was on polynomials. So that's the procedure we are going to follow. Are we
Okay,
together?
sir. Yes, sir.
All right. Now let's take the next example here. We want to look for this limit at x tends to 0. So as x tends to 0, this limit also gives us 0 over 0. These are normally cases of L'Hopital's rule, but there are other ways in which we can adjust them. So if we expand this numerator, we will have 36 plus 12h plus h squared. Now minus this 36, we will be left with 12h plus h squared. And we can factor that one out. If you factor this one out, because these two will cancel out, when we factor it out, we'll be left with h into 12 plus h. Now this h can cancel out this other h here, and the limit now as h tends to 0 will be equal to 12 plus 0, which is equal to 12. So all the notes on limits have been uploaded, and the other ones on further maths, as Adelaide and the other lady were asking, they'll be online latest at midnight, I think so. So they can actually get to those videos, lessons, as I can call them. Okay, let's take the next question. Let's take the next. So the next question is this. We have evaluate this limit. So this limit is a very technical limit, but we can factorize the denominator. Yes, the denominator can be factorized in this limit, and we can equally solve. Or we can follow the procedure that is here, it will still be okay. So we can do this as the denominator can be factorized as root z now. Root z minus 2, because it's like a difference of 2 squares. All that over, or all that into root z plus 2, right? And this root z here minus 2 will cancel out. This one will cancel out this one. Such that we will now be left with 1 over root z plus 2 when you cancel out. And we can now obtain this limit. So this is exactly what they have done here. So another way to do it is to multiply the numerator and denominator by the conjugate of this numerator, that is by root z plus 2. And when we multiply by root z plus 2, this is the same result we obtain. And we can now take the limit as x tends to 4. Note that we consider the positive square root of this z, which is plus 2. And the limit here gives us 1/4. This type of limits are very, very common in past GCE equations, advanced level. Are we together?
Yes, sir.
Okay. Let's move on to the next. Even if you cannot get this lesson is live. At the end of this lesson, if there's anything you had issues with, you can go to YouTube, our channel GCE Maths Panel, and you play back this video. You get the results from there, exactly as you are watching. You see it back. All right, let's look at the next one. We are moving from simple to complex. This type of limits are common for industrial students and in further maths. So with this type of limits, what we will do is we will just multiply numerator and denominator by, you just take this numerator, change the sign here, plus 4. And then multiply numerator and denominator by that and simplify. So that's what we have done here. So we have multiplied numerator and denominator by root 2x plus 22. That's all of that in the root. Then plus 4 outside. We multiply numerator and denominator by that. And we simplify. When we do this simplification, at the end, we are left with 2 over root 2x plus 22. That's all of that in the roots, and then plus 4 outside. That's what we obtain at the end after all of this simplification. And when we now take the limit as x tends to minus 3, the limit here is equal to 1 on 4. The limit to give us 1 all over 4. Guys, are there any questions? If you have questions, you can ask us as we move ahead with this lesson.
There's no question,
Sir,
sir.
what is
Yes,
the
please.
sign of 20?
Can you speak?
I mean the conjugate of the numerator.
Yeah, the
It's only
conjugate.
the sign of.
Yes, it's just this one. This all of these things inside the root is considered as one number. So the conjugate is just to change the sign between what is inside the root and what is not inside the root. Okay?
Okay, sir.
Yeah, you're welcome. So when we change it and we simplify, that's what we obtain. Yes. Ask a question.
On the question, can we still use the
Your network is disturbing. Please, don't stop moving. Yes, your network is really disturbing.
Can you get me, sir?
I'm getting
Yes,
you now.
I want to ask you if you consider the capital to.
All right, let us see. You say you want to see if you can use L'Hopital's rule. Let us see what
Okay,
happens.
let me just ask that one.
Mhm. Yes, please. All right. Normally, if I have to differentiate, let me show you something from this equation which you have asked. If we differentiate the numerator and differentiate normally, L'Hopital's rule should be the last thing you should apply after you have tried all methods and they fail. But in this case, we are using L'Hopital's rule. We differentiate the numerator here. What are we going to have? We are going to have the numerator, we differentiate the core. We'll have 2, and then into 2x.
Sorry.
Yes, I'm coming, please. 2x plus 22 to the power a half minus 1. What's a half minus 1? A half minus 1 is minus a half. And all of this now times a half. So this one times a half. So this is what you have, right? For L'Hopital's rule, when you differentiate the denominator, we will have 1. This is L'Hopital's rule. This will cancel out with this one. Now when we put minus 3 here, what is going to happen? 2 times minus 3 is minus what? Minus 6 now. Plus 22. What does that give us? 16. Now the square, what's the square root of 16? That gives us 16 now. So 1 over the square root of 16 gives us 1 over 4, right? Yes, because it's the power negative we have. So we have the same result. We have the same result. And you use the L'Hopital's rule here because minus 3 times 2 is minus 6. Minus 6 plus 22 is 16. 16 minus 4 is 0. I'm sorry, root 16, that which is 4 minus 4 is 0. So this limit gave us 0 over 0. So that's why we use L'Hopital's rule, which is still okay. So we can still use this method without using L'Hopital's rule, okay, Rodrigue? So L'Hopital's rule is okay. Are we together?
Yes.
Yeah. All right, let's move ahead. Rodrigue, I think your connection is really disturbing, eh? Now, what about this other limit as
Yes,
x
sir.
tends to 0? You can still use a L'Hopital's rule here now because this will give you 0 over 0. So we have the right to use L'Hopital's rule. Otherwise, you can still use the conjugate of this, multiply numerator and denominator by it, and then we will have the same result. Are we together? So the most important thing is to know what to do. What do I do here? Or what should I do here? If you already know what you can do there, then there is no need for us to continue with the solving, except you solve and get stuck. Then you can now bring your question and we discuss it in class. But now we just need to know what do we do in this case so that we can do it faster and do it accurately. That is what we actually need.
Yes.
All right, let's take the next question. So we have this. To evaluate the limits if they exist. To evaluate the limits if they exist. So please look at this very well. Look at this question very well. Some messages are coming. I don't need to see them. They are coming. I cannot see from the computer. I only see from the phone. All right. Have you gone through? Okay. So with this, we have a function that is periodic or defined with intervals. That is defined with intervals. And we can obtain or we can solve this type of questions looking for the limits from the left and from the right to see if the limit exists. So with this, if they ask me to look for the limit as x tends to 1, I have to make sure I get the left limit and the right limit. If the answers are not the same, then the limit does not exist. So the limit here as x tends to, for example, minus 6, I substitute in the function to the left, that is the first one. I also substitute the same value to the function in the right. And you see that the two values will be the same at the end. That is 7 minus 4 times minus 6, that gives us plus 31. And 6 squared, that is 36. Sorry. And here we have, that's minus 6 squared. Minus 6 squared is 36 plus 2. What does that give us?
38.
Alright, let's see 38. So in that case, if the limits on both sides are not the same, because we have 31 and 38, that therefore means that at this point x equals 1, this function is not continuous. Or at x, as x tends to 6, this function is not continuous at the point x equals 6. The limit does not exist. Let me just take the example of the second one where x tends to 1 from above and from below. As x tends to 1 from below and from above, for the below we have 7 into 7 minus 4 into minus 1. The limit is 3. For the limit to the right, we have 1 squared plus 2, which is also 3. Since the limit to the left and limit to the right are the same, if the function is continuous at this point x equals 1. But what about the point x equals 6? Shows that the function is not continuous there now because the two limits to obtain are not the same. Or should we check? Let's see 7.
So I don't really know what it means.
Yes.
Hello? Yes, sir, I don't really understand what it means by for a. Are you getting me, sir?
I'm getting you. Right on.
Yes, what it means for the limit above and below. What does it really mean, sir?
Limit above and below, or limit to the left and to the right. All right. If you look at the last 2 videos that have been uploaded, or if you look at the notes that are on the blog GCE Math Panel, this has been explained there very well, and I've even used diagrams to actually explain the issue of limits to the left and to the right. Let me see if I can show you something. Let me go online. Okay, let me open this page and see. Okay, please let me just go there. Okay.
Yes, sir.
Limits to the left and to the right. This is advanced level.
Is there a difference between limits to the left and to the right and above and below?
No, it's the same thing. Limit to the left is limit from below. Limit to the right is
Okay.
limit from above.
Okay, sir.
Was that your question?
No.
All right. So limit to the left, either you say left and right, or you say below and above. Where below is left and above is right. So those are the terminologies. Okay.
Okay, sir.
Yeah. Let me just try to get to this. I think that's chapter 7. Chapter 7. Chapter 7c. All right. Here we have the notes on limits to the left and to the right of a function. And now look at. Can you see this graph here?
Yes, sir.
Look at this graph. This is the point x is equal to 1 now. This is the line x equals 1. And for this line
Yes, sir.
x equals 1, this function is not defined along this line because this line is a vertical asymptote, right?
Yes, sir.
So we want to know how this curve will behave immediately above this line and immediately before this line. That is immediately below or to the left and immediately above or to the right. Look at it. Immediately above or to the right, that x tends to, the curve is moving to infinity, plus infinity. But as x tends to 1 from below or to the left, the curve is moving to negative infinity. Can you see?
Yes, sir.
So this is the idea of limit to the left and to the right. Look at this. The limit to the right here is positive infinity. Limit to the left is negative infinity. This is chapter. If you look at chapter 7c, you'll see how this has really been explained there very well. So this is the concept of limit to the left and to the right. We want to know how the curve behaves immediately above the vertical asymptote and immediately below the vertical asymptote, if it's actually this type of function. But if it's a periodic function like what we are seeing now, we want to know how it also behaves for that periodic function. So those are the concepts of limits to the left and limits to the right.
Thank you, sir.
All right, you're welcome. So that's what we are looking at here now. This one now is a periodic function. This first part of the function up to 1, you can see x is less than 1. This is like to the left. Therefore, x greater than or equal to 1, this is now to the right. So, for example, if you are looking at b here, we want to look for the limit of f of x as x tends to, let us consider b, as x tends to 1. We can look for the limit as x tends to 1 from below. This negative sign here means from below or to the left. Why this positive here means from above or to the right. As x tends to 1 from below, we use the first function, first part of this function. So we'll have 7 into 4, that is 7 minus 4 into 1. That limit gave us 3. Then, as x tends to 1 from above, we use the second function now, this second function here. We use 1 squared plus 2. The limit still gave us 3 now. So from it, we conclude that the limit of f of x as x tends to 1 from below is equal to the limit as x tends to 1 from above, and all the answers are 3. So we know that in this case, the limit exists. The limit exists because 1, the limits are not equal to infinity. The first one is not infinity, the second one is not infinity. Secondly, the two are the same. Since the two are the same, we say the limit exists. If the limits were different, so that the limit does not exist. Because the limit of a number is unique. It cannot have two different values. Is that okay?
Yes, sir.
Yeah. So can we go ahead?
Right answer.
Okay, let's write down. Alright, the next question. So the next question is this. And we have h of z is equal to that. We have h of z is equal to that. It's defined for z less than or equal to minus 4 by 6z. And for z greater than minus 4, we have 1 minus 9z. Evaluate the limits if they exist as x tends to 7 and as x tends to minus 4. So we are going to use the same idea because this one is a periodic function. So it's an interval function. So as x tends to 7, what will be the limit? You can see that 7 does not actually have a problem here. You can just look for the limit as x tends to 7 to be equal to, which interval do we use as x tends to 7? The first part of the function or the second part?
First part.
The first part?
Yes, sir.
Yes, I think we should use the second part instead, because if you look at this first part, 7 is not in this interval now. Z here is less than or equal to minus 4. So we cannot use this first function. But look at the second function. We use this one when z is greater than minus 4. So question, is 7 greater than minus 4?
Yes, sir.
It means that we are going to use the second part of the function to obtain this limit. And this will be 1
Yes,
minus 9 into 7. That gives us minus 62. Are we together?
Yes, sir.
Alright, now let's look for the limit as x tends to 4. If you look at this 4
Yes,
now,
sir.
4 is some sort of a boundary. Because you use this part when z is less than or equal to minus 4. And this other one when infinitely greater than minus 4. So this 4 is some sort of a boundary. So we have to look for the limits using the two functions since 4 is a boundary and see if the answers are the same. Just like the previous question. So the limit of h of z as z tends to minus 4 from below this first function, that will be equal to 6 into minus 4, and that gives us minus 24. Now the limit of h of z as z tends to 4 from above now is the second function. That should be 1 minus 9 into minus 4. That gives us 37. Are the two limits the same? That's the question.
They are not.
They are not. So
No,
now,
sir.
since they are not the same, does the limit exist?
It doesn't exist.
Good. So the limit does
No,
not
sir.
exist when the two are not the same, or if the two give us infinity. So when the answer is infinity, we say it does not exist. And if the two answers also are not the same, we say it does not exist. So that is the idea.
That is, it exists only when the two are the same.
Yes, only when the two are the same and the answer is not infinity.
Okay.
Yes, if we are working at a boundary, like this 4 here, minus 4 is a boundary here. Unlike this 7 that we use, 7 was not at the boundary point, as you can see. Yeah, because this minus 4 here is like a fence. Either you're on this side of the fence or on the other side of the fence. But this 7 does not appear here in these intervals of definition. Okay, now let's look at you and evaluate this limit if it exists. Evaluate this limit if it exists. So with this limit, as x tends to 5, you can see you can just do it directly now. 5 minus 5 is 0 plus 10, 10. So this limit is 10 as x tends to 5. Though we can still break down this absolute value, a part of the function, into x minus 5 for x greater than or equal to 5 and minus into x minus 5 for x less than 5. Can break it down there, but the answers will still give the same thing. There is no need. Okay. All right, next question. We have this limit if it exists as x tends to minus 1. As x tends to minus 1. So normally we can break down this denominator as well, as you can see, t plus 1 for t greater than or equal to minus 1, and minus into t plus 1 for t less than or equal to 1. And as t tends to minus 1 from below, this minus 1 from below, we are going to use this second function. So we fit in minus 1 here. Minus 1 plus 1 is 0. So we have minus 0 now. And then for the numerator, minus 1, so we have 0 over 0. So we can still apply L'Hopital's rule. If we apply L'Hopital's rule in this case, since it's 0 over 0, we will now have minus 1 over minus 1. When we differentiate, we'll have 1 over minus 1. Then on the right, as it tends to minus 1 from above, we are now using the t plus 1. Minus 1 from above, we use t plus 1. In fact, we use it directly as it is like this. And that limit is instead going to be plus 1. So for below, we have minus 1. This is minus 1 from below. Then from above, when you put the limit, we'll have plus 1. So from below, we will have the limit like this. We'll have t plus 1. All this over, and this second part of the function shows from below. All this over minus into t plus 1. This one can cancel. When you cancel out, what do we have? Minus 1, right?
Negative 1.
Minus 1. So this 1 is from below. And then now from above, we use this other function from above. We will have t plus 1. All that over t plus 1. This t plus 1 is this numerator of this function since it does not change. Now this denominator, since it's absolute value, we have to break it down like this. And when we cancel out these 2, what's the answer? 1 now. So this is the limit from above. It is 1. The limit from below is minus 1. The two limits are not the same. So the two limits are not the same. As the two limits are not the same, you see the limit does not exist. Are we together?
Yes, sir.
Yes. So I employ an indulgence that you go through the limits chapters again from chapter 7a to chapter 7e. These limits are very, very important because in chapter 8, we will be using most of these limits in differentiation. And when we also come to curve sketching in chapter 8, we'll use all of these limits, the curve sketching. In chapter 8, we'll look at curve sketching for logarithmic, exponential, rational, radical, all those functions. We'll look at curve sketching again there. That is the next chapter. That is immediately after differentiation. Because the chapter is differentiation and curve sketching. Alright, let's move on. Now look at this type of limits. This type of limits follow what we call the Sandwich Theorem. the Sandwich Theorem, and I've covered this Sandwich Theorem in chapter 7e. You can see the Sandwich Theorem there. Now here I've been told that given that 7x is less than or equal to f of x and less than or equal to 3x squared plus 2 for all x, determine the limit of f of x as x tends to 2. As x tends to 2. Now, if the limit from below, that means using this part of the function, and the limit from above, that is this other part of the function, are the same, then it means the limit of f of x is that value. So I'll look for the limit of 7x as x tends to a number. Also look for the limit of 3x squared plus 2 as x tends to that same number. If the answers are the same, then that is the limit of f of x. For example, let us find this limit of f of x as x tends to 2. So I'll use the function that is less than. That will give me the limit of 7x as x tends to 2 will be 7 times 2, which is 14. Then the limit of f of x using the second function, now this one above, as x tends to 2, you have 3 into 2 squared, that's 3 times 4, which is 12 plus 2, 14. So this gives us 14 now.
Yes, sir.
Now the two limits are the
Yes,
same,
sir.
right?
Yeah.
Yes, sir.
Yeah. Since the limit from above is equal to the limit from below, then we see the limit of f of x is 14. This one is called the Sandwich Theorem, and others call it the Squeeze Theorem. Some even others attempt to call it the intermediate value theorem. So therefore means that the limit of this function is 14. Whenever you see this type of case, this is what you do. Are we together?
Yes, sir.
Yeah, so these limits
Yes, sir.
below and the limit above should be the same. When the two limits are the same, means the one in between is having that same limit. I love this one so much. Alright, let's look at another example with this one. This one is also a tough example. Now look for this limit. You want to look for the limit of x to the power 4 sine pi on x. This one is also a very, very good thing. You are going to use the intermediate value theorem or the Squeeze theorem as well. And this theorem is very, very important when you're looking for the maximum or minimum value for trigonometric functions. So the first thing we have to understand is that the sine of any angle has a maximum value of 1 and a minimum value of minus 1. Look at this is what I'm talking about. So the angle there is pi on x. It doesn't matter what the angle is, we don't care. But we know that the minimum value of sine anything is minus 1. The maximum value of sine anything is plus 1. Now this is the sine pi on x that we have here. So if you multiply all through by x to the power 4, this is what we will have. Minus 1 times x to the power 4 give us minus x to the power 4. Then here we have x to the power 4 sine pi on x less than or equal to 1 times x to the power 4. This is what it gives us. Can you now see the Squeeze theorem here?
Yes, sir.
The Squeeze
Yes,
theorem appeared. Now we look for the limit as x tends to 0 of this function below. That is of this minus x to the power 4. And also look for the limit
So then
of
what is x to the power 4 still doing inside?
where?
Yeah. So,
No, you have to multiply everything now by x to the power 4. Hey, my brother, this is equation. So look, the equality sign is there. Anything you do to anybody, you must do the same thing to everybody.
I'm asking then, when you multiply with x to the power 4 not be eliminated from the inside the interval.
We are trying to make this function to look like the Squeeze theorem function. Look at this place. Look at this place. I'm going to put a box. This is the limit you are looking for, right?
Yes, sir.
Now, if we have the limit of this one, look at the limit below it and the limit above it. If these two answers are the same, then we automatically have the limit of this one in between. That is squeezed in between. Do you understand?
Okay, sir. Yes, sir.
If you look at
Yes,
the
sir.
extreme right, look at the extreme right. This is the limit you are looking for at extreme right. So we are using the Squeeze theorem. And this x to the power 4 sine pi over x, this is it here. So it therefore means that if you have the limit of minus x to the power 4 and limit of x to the power 4, if the answer are the same, then we automatically have this limit because this limit must have that same answer. Now let's look at this one. As x tends to 0, minus x to the power 4 is going to be equal to 0. And this other one here, when you fit 0, you're also going to have 0. Now the limit
0.
below is 0, the limit above is 0, right?
Yes.
So this is our conclusion.
Yes, sir.
Therefore, this limit that we are looking for like this is equal to 0. This is our conclusion. So we are using the Squeeze theorem to solve that question. So you can now see why we needed to have done that. The first thing to look at is since we identify the sine function, we know that the smallest value of the sine function is minus 1 and the highest value is plus 1. But this sine function, they have multiplied it here by x to the power 4. So I will also come here and multiply everything by x to the power 4. So I'll also come here and multiply everything by that x to the power 4, which is exactly what I have done here. When I do that multiplication, it is going to give me these results that we have. That is why we have these particular results, okay? Okay. Okay, now we are looking at what the Squeeze theorem is all about. So the Squeeze theorem indicates that the Squeeze theorem, if we have the functions f of x, g of x, and h of x, which are all defined, where x is not equal to a over an open interval containing a, if for all x not equal to a in an open interval containing a, and where L is a real number, then the limit of g of x as x tends to a is equal to L. So this is what the Squeeze theorem is just talking about. If the limit of f of x is equal to the limit of h of x, therefore the limit of g of x is having the same value. This is the Squeeze theorem, which we have just looked at. It's an application of that Squeeze theorem. So if this limit of f of x is having the same value as the limit of h of x as x tends to a, which is equal to L, therefore the limit of this one that is squeezed in between is having that same value as x tends to a. So that is the Squeeze theorem. So we are now moving to the L'Hopital's rule. So L'Hopital's rule provides a method for evaluating limits of indeterminate forms of the type 0 over 0 or infinity over infinity. This type of limit we use L'Hopital's rule. And this L'Hopital's rule is telling us that the limit of f of x as x tends to a is 0, and the limit of g of x as x tends to a is also 0. And then the limit of f of x on g of x as x tends to a is the same as the limit as x tends to a of their respective derivative quotients, of the quotients of their derivatives. Equally, if x is also turning back to infinity, like in this second case, we'll have a limit of the form infinity over infinity. We can still also apply L'Hopital's rule. So we apply L'Hopital's rule when we have indeterminate forms like 0 over 0 or infinity over infinity. So in this part of the lesson now, we'll mostly look at applications of L'Hopital's rule. Alright, review this type of function now is mostly for people who are doing technical, this first one. So the limit of this function as x tends to 0 will give us a to the power 0, which is 1 minus 1, 0 over 0. So this has given us 0 over 0, right?
Yes,
so
sir.
we have to apply L'Hopital's rule here. In applying L'Hopital's rule, we differentiate numerator and denominator. Whenever you differentiate a to the power x, you have a to the power x ln a. We will see this in the next chapter. We are sorry that we are taking this. Normally, after the next chapter, you're supposed to take this again. But it's good that we just trash it so that when we get there, we know that there are some things that we have left undone. So whenever you differentiate a to the power x, according to L'Hopital's rule, you have a to the power x ln a. When you differentiate a constant, you have 0. That's why 1 has disappeared. When you differentiate x, you have 1. So we can now look for this limit as x tends to 0 of this function. So we now have a to the power 0, which is 1. 1 times ln a. So this limit is equal to ln a. This limit is equal to ln a. After the next chapter, we'll still look at some of these things again because I'm sure that some of the things students would have forgotten a bit. So we'll still look at them. Then we have this other limit here as x tends to 2. This is another application of L'Hopital's rule as x tends to 2. If we fit 2 into that into this function, you have 7 plus 2, 9. Square root of 9 is 3 minus 3 is 0, and denominator is 0. So in this particular case, we still have to apply L'Hopital's rule. When we differentiate this numerator, we are going to have 1 over 2 root 7 plus x, like this. As I've said about this differentiation, don't worry so much. We'll look at them again in the next chapter because the next chapter is on differentiation. But just understand what you are supposed to do when you find a case like this. When you differentiate the denominator, you will have 1. This is the 1 here. You can now take your limit here. Limit will give you the value to be equal to 1 over 6. 1 over 6 as the limit. I actually pray you to also that even at the end of this video, watch the video again. Because I think I might even be going very fast. You can even slow the speed on your phone. Take the time again and go through this video. I don't know if the notes are uploaded, they'll equally put it on the system, but I don't know. As for the other notes which have not been there, they are there now. This is another case. As x tends to 2, this one will also be undefined. You equally have 0 over, okay, this is 4 over 0. This is 4 over 0 minus 1 over 0. So you have infinity minus infinity. So with this type of function that we have infinity over infinity like this, we have to transform them to either have the L'Hopital's form of 0 over 0 or infinity over infinity. Because infinity minus infinity, you don't know the answer. It's not defined. It's not clear. So you have to transform it to have the form of 0 over 0 or infinity over infinity. So what do we do here? We can look for the common LCM first of all. We look for the LCM here. And you see that when we bring them together, we have 0 over 0 at the end. Now this is in the form of L'Hopital's now. So just by looking for the LCM here and simplifying, we have 2 over x squared minus 4. And this limit gives us 0 over 0. So we can now differentiate. When we differentiate 2 minus x, we are going to have minus 1. And when we differentiate x squared, we have 2x. We apply the limit now as x tends to 2. This limit gives us 1 on 4. The limit gives us 1 on 4. Any question at this point? Any question at this point? Or it's getting tough?
None, sir.
No, sir.
I don't know why the other guys are not online today. They're only waiting maybe perhaps for Monday. Well, I think the others are watching from YouTube instead. Oh yeah, I can see some guys are watching from YouTube instead. Okay. Then we equally have this other limit. The next one. This other one. This one is common also for industrial. So you can just apply L'Hopital's rule here. You have 2x over 2x ln 2, just like the other one I showed you, 8 to the power x. You differentiate it, you have 8 to the power x ln a. So it's the same thing here. You have 2x over 2x ln 2. But this will still give you infinity over infinity. So you differentiate again. So even if you have infinity or infinity, you still apply the L'Hopital's rule. You have infinity or infinity, you continue, or 0 over 0, you continue until you not have it again. So here now, when we differentiate now for the second time, we will have 2 all over, that is, we have 2 over, yes please, okay, yes, I get it. So when we this one, this 2 over ln 2 is a constant, so we have x over 2 to the power x, right? So we can bring this 2 in front over ln 2. We differentiate this, we'll have 1 over 2 to the power x ln 2. So we have 2 over ln 2. The derivative of this one will now give us 1 over 2 to the power x ln 2. The 2 to the power x of x tends to infinity is infinity, and 1 over infinity will give us 0. So all of this one here gives us infinity, 1 over infinity gives us 0, and 0 times all of this, 0 times any constant, this is a constant, is equal to 0. That's why this limit here is equal to 0. Just by looking at this also, just by observation, you know that 2 to the power x increases faster than x squared. So as x tends to infinity, this limit is 0. By observing, when you solve most of these things, you just look at the sum and you see the limit directly. So that is it. Now there are some limits that involve logarithms. Now this one is mostly for those who are doing technical, industrial, and those who are doing further maths. Adelaide, are you doing further maths or is it Lina?
No, sir.
When you go to the university, you meet this type of limits, eh? So for limits that have the forms infinity to the power 0 or 0 to the power 0 and all of those sorts, we can proceed by looking for their limits using logarithm. For example, this limit as x tends to infinity, you will have the infinite root of infinity, which does not make sense. So this thing, first of all, is that let y be equal to t root t to the power 3. You now take ln on both sides. Can you see? You take ln on both sides at this point. You now take ln on both sides. When you take ln on both sides, this will give you for this side. This one is the same as t to the power 3, all raised to the power 1 over t, because this is the th root. The th root means to the power 1 over t.
Yes.
So this is equal to the ln of t to the power 3 times 1 over t is 3 over t now.
Yes,
sir.
sir.
Now, according to the laws of logarithms, we can bring this power in front. This will give us 3 over t ln t, which is the same as 3 ln t on t. So from this point, this ln y is equal to 3 ln t on t. Now, for the left hand side, or maybe on the right hand side, as x tends to infinity, this one as x tends to infinity, here. As x tends to infinity, we will have infinity over infinity. And we can apply L'Hopital's rule now for this right hand side. So we differentiate the numerator and differentiate the denominator. When you differentiate ln of anything, is equal to the derivative of the core over the core. So if I differentiate ln t, it will be 1 over t. So that will give me 3 times 1 over t. So this is it. 1 over t. When I differentiate t, the answer is 1. So this now gives me 3 times 1 over t, which is 3 on t. This, I'm still working with the right hand side. 3 on t, as t tends to infinity, that is 3 over infinity, which is 0 now.
Yes, sir.
So now for the left hand side, the limit of y as t tends to infinity will be equal to, that will be equal to 0 now.
Yes, sir. Yes, sir.
Yeah, so the limit of y, because this is the left hand side now. Look at this left hand side. The limit of ln y as t tends to infinity, this answer is equal to, because the right hand side, the answer we have is 0. So from here we can solve for y. From this point now, you have ln y is equal to 0. Therefore, as t tends to infinity, y will be tending to what? E to the power 0.
Yes.
Is equal to 1.
Equals to 1.
Then that's why our answer here is equal to 1. So you take ln and you work with both sides whenever you have this infinity to the power 0 or 0 to the power 0 or 1 to the power infinity. All those type of limits that have power, you have to use logarithms to get their limit. Do you get me? Yes, all those limits that
Yes,
have
sir.
to the power 0, power infinity, power anything, you have to use logarithms for their limits. You need to use logarithms for their limits. Okay, let us look at the next question. This is another one. So for this particular question also, we see that we are equally going to have that infinity over infinity stuff. So here we are looking for the limits of 1, that's x to the power 1 over 1 minus x as x tends to 1. Normally this will give us 1 to the power infinity. This will give us 1 to the power infinity. So these are the limits that we have to use that logarithm stuff. So we'll say let y be equal to this x to the power 1 over 1 minus x. We now take ln on both sides. Ln y be equal to ln x over 1 minus x. We bring this power in front. It will be 1 over 1 minus x times ln x, which is the same as ln x over 1 minus x. At this point, if we take infinity here, it will give us infinity. Infinity with the denominator, it will still give us infinity. So for this right hand side, we are going to apply L'Hopital's rule. So we are going to differentiate. To apply L'Hopital's rule, differentiate ln x, we have 1 over x, we have 1 over x here. Now we differentiate 1 minus x, we have minus 1. Now as x tends to 1, this right hand side tends to minus 1. So the left hand side is still the same. So this, all of this is equal to 1. The answer is equal to 1. So from here now, we can look for y now. We can solve for y because this one now is the same like the equation ln y is equal to 1. Sorry, it's equal to negative 1. So our limit there is negative. So from here, since I've written ln, it means that the base here is e. So as x tends to 1, y tends to e to the power minus 1. And e to the power minus 1 is equal to 1 over e. Roger, are we together?
Yeah, together, sir.
Even when you have to go and write your concours or whatever after this back class or upper seat, these are all the things that you'll be learning. So when you run away from these things, you still meet them again. That's the good news.
We cannot.
Yes, when I just left school, things were tough. I had to be doing all of these preparatory classes, and this is what I was teaching and teaching and teaching. I used to have some money for my pocket. Yeah, I was running from one side of the town to another side of the town, and
That means
it really
when you
helped.
know them, you're already rich.
It doesn't mean they're rich now. You know, most of the people who have book like this, they don't have the money.
That's true.
And they have to use their head and do something else. So this is another case of the same thing. We still use the same thing ln here. We differentiate and we apply. We are going to obtain this value. The limit here is equal to 1. It's the same procedure. I would like you to look at that same procedure at the end of these tutorials. It is very important. So we have already been live for 1 hour. We already come to an end. What about this one? The limit of this one as x tends to 0. This limit will be equal to 0 over 0. In fact, as x tends to a very small angle, as I saw in the previous class, x over sine x is equal to 1. As x tends to 0, as x approaches 0, x over sine x is equal to 1. Even if you write it as sine x over x, the answer is still equal to 1. So this limit don't need to solve. It's a standard value. The answer is equal to 1. And you usually use this when you are balancing things in trigonometry to get the limit. Lina, you should take very good care of this one. You should take note of this one so much. This one will apply more to you.
Okay.
This one is the same thing. We have to balance it such that the angles will be the same. So this is what I'm going to do. This is sine 2x now. I'm going to balance. This is the form of what I'm going to do to use to balance. I will make sure that the denominator has this same angle like this. So for the denominator, I'll write 2x. Can you see? I'll multiply numerator and denominator by 2x so that I can cancel out. This one can now become sine 2x. Oh, sorry, my pen is really having problem. You have sine 2x over 2x times 2x over 3x. Can you see? I want to, because when the sine of an angle over the angle, the sine of an angle over the angle as x tends to 0 is equal to 1. So all of this is going to give me 1. That's what I want to do. Now this other 2 can cancel out, so x will cancel out x, and this limit will be equal to 2 on 3. That's why the limit is 2 on 3. Lina, are you okay?
Yes, sir.
Good. This one concerns you more than Roderick. This one concerns you so much. Then the next one is a similar thing. Let me clean this. This is the same thing here. I know that this my x squared minus x minus 2 can be factorized as x minus 2 into x plus 1.
Wow.
Yeah, but the limit as x tends to a very small number, 2 is a small number. It's approximately the same as sine x minus 2 over x minus 2. This one will just give us 1. This one is equal to 1. Because the angle over sine of an angle over the angle, this one is equal to 1. Oh, sorry, it's equal to 1, not 0. So we are now left just with 1 over 2 plus 1. 1 over 2 plus 1 is equal to 3. So we have 1 times 3, which is 1/3. These are algebra tricks in trigonometry. Then here we have many of these other ones. There are many of them here. Let's look at the first one. This is sine 3x on x. So I'm just going to do some balancing so that I'll have the answer directly. I know that the sine of any angle over that same angle is 1. So I can just put 3 here now. So times 1 over 3. Or I just put 3 here. Now balance it by multiplying this numerator by 3 so that I cancel out. Now, sine 3x over 3x, the limit of this as x tends to 0 is equal to 1. 1 times 3 is equal to 3. That's what they have done here. So sine 3x on x is equal to 3. Can you see? They've put 3 here and they've cancelled 3 divided by 3. So that sine 3x now on 3x is equal to 1 times 3, which is 3. It's the same thing here. So I can just multiply numerator and denominator by 3. I'll put 3 here and also put 3 below. This one now is the same as sine 3 theta. Let me replace this. This 2 is now at this position. So you have sine 3 theta on theta. This is equal to 1 times 3 on 2. 3 on 2. That's what they are doing here. It's the same thing with this one. Sine x on x 1. And sine x on x as x tends to 1 0 from below. Normally the angle is going to be negative. That's why this one is equal to negative 1. Normally the limit of sine x on absolute value of x does not exist, because the limit from below is not equal to the limit from above. These two limits are not the same. So whenever you see the absolute value sign, be very careful with the limit. Whenever you see the absolute value sign, be very careful with the limit. Are we together?
Yes, sir.
Okay. Do you have younger brothers or friends who are writing physics ordinary level, economics, and chemistry?
Yes, sir.
Yes, I am. I heard that some videos have just been uploaded for ordinary level physics and chemistry and so on. I am still to check, but I just heard. But I've seen the one for physics. I've seen it. The others, still waiting for the information. I'm like the spokesperson of the house,
Mm.
Minister of
Then what
Communication.
about
What about?
biology and chemistry for advanced level?
I'll also check and see. Also check and see. There were some videos that were online about 2 or 3 years ago. I'll still check immediately after this. I'll check, please. Yeah, very important. Now, so you can equally look for each of these other limits now. Sine 2x on this, and cos 2x on this. As x tends to 0, we don't need to use L'Hopital's rule here. As x tends to 0, sine 3 times 0 is 0. So sine 0 is 0. Cos 0 is 1. So this limit is direct. The limit is 0. Because 0 divided by 1 is 0. But some people see this thing, they'll just be afraid. Just put it directly, you'll see the answer coming out. Even this other one below, the limit is also the same. As x tends to 0, cos 0 is 1. Divided by cos 0 again, which is still 1. 1 divided by 1, the limit is 1. This one is very easy. But it looks very frightful. One step. Then, find the limits of each of these other ones. We are equally going to use the trick here. We know that t cubed plus 3 squared is the same as t plus 3 into something. So that's the idea we use here. Sine t plus 3 over t plus 3. This sine of this angle is going to give us 1. And we are left with t squared outside the bracket. This will cancel out. So we are left with, as x tends to minus 3, minus 3 squared is 9. So we have 1 times 1 over 9. This limit is 1 over 9. It looks very frightful, but it's very simple. What about this other one of x cot 2x? Cot 2x is just the same as cos 2x over sine 2x. Very easy. So you just write x times cos 2x over sine 2x. And as x tends to 0, or what can we observe here? We can see that this x over sine 2x, we can manage it in such a way that we can have 1. So we can multiply numerator and denominator by 2, as you can see here. Instead of writing x, I'll write 2x. And I'll divide it again back by 2. So this part now is going to give me 1. And this other part will give me cos 0, which is 1 on 2. Is 1 on 2. So 1 times 1 on 2 is 1 on 2. Very easy. The trick is that at the end of this video, it's good that you solve everything again. At the end of each class, solve everything and then get more questions and solve. You see that everything is just ABC. Even at the end, maybe at the end, you may not even need this mathematics to succeed in life and so on. Because some people end up selling their interests in the market and they will make money. Rodrigo, the most important thing is to have money now. There's no need knowing math that they don't have money at the end. It doesn't make sense. Just like somebody with 25 points who does not have a job. That's rubbish.
Ah.
So these are the same things here. This limit as x tends to infinity. These are the same procedures that we can follow here. This will give us sine 2x on 2x times 2. That's giving us 2. The same stuff here. See how they've arranged it now. Whenever you just arrange like that, you see the answer coming out. And you have your results. No stress. So if you solve this once again, look at them, solve them. Don't take all these simple examples. Some people start the example the teacher gives is always easy. If the teacher takes the most difficult example and solve, that example becomes easy. These other ones I have already shown you in the past tutorials. You can look for the value of k. You just have to look for the limits to the left and limits to the right and equate them if it is continuous at this point. And you automatically get the value of k. You can equally solve all of these ones to find the value of k too. This is another example of find the value of k if it is continuous at x equals 3. At the end of this lesson, solve this question. This is the answer here already, but solve it again. We have done most of these ones. There's no need to be emphasizing again so much on this. Another example, the same thing. Solve it again. Find the value of k if this function is continuous at x equals 2. Limit from below should be equal to limit from above. That's the idea. you just jump into solving it. Even this one, you already know the answer is equal to 1 because the sine of an angle over the same angle is 1. The answer is there, clear. This one you can see, you can actually do some magic like we have done here. Sine 4x on 4x times here we can take 5x on sine 5x. The answers will be 1 1. Then you do see I can do some adjustments. 4 and 5 have appeared, so you adjust, you balance until you come to this solution at the end. 4 on 5. This one the same thing, you can simplify, you can break down stuff. Tan 3x the same as sine 3x on cos 3x. That's what they have done here. And this sine 3x over sine that, you can actually simplify like this. Look, I've broken it down into 3 here. Sine 3x on x times this one, look at the opposite here, the power minus 1, that's the reciprocal now, times 1 over cos 3x. The answer will be 3 at the end. In fact, from here you can see it directly for very small angles. This thing is approximately equal to just this angle divided by this one, 3x over x, which is 3. That's the shortcut I did not want to tell you. I wanted you to follow these procedures that you understand before you can use the shortcut. For very small angles, as x is tending to 0, you can forget about the tan. Just take the 3x divided by x. Forget about the sin, forget about the tan. Just take 3x divided by x gives you the limit. The same with this one behind here. For very small angles, forget about the sign here, forget about the sign here. 4x divided by 5x is 4 over 5. That's why the answer is 4 over 5. Because the angles are very small. For very small angles, sine 4x approximately equal to 4x. Do you get do you see the tricks?
Yes, sir.
Yes.
Yeah.
So this is approximately equal to 3x on x for very small angles because that's for the sine. Sine and tan behave the same for very small angles. Cosine behaves opposite. So since I have the tan and sine here, I know their behavior already. As x tends to 0 for this one, it's going to give us 0 over 0. You can apply a L'Hopital's rule still. You know how you can adjust this one as well. Yes, you know how you can adjust this one. And since the angle is very, very small, you can forget about the sine. This one is the same as sine 5x all squared now. So this one is sine 5x times sine 5x. So forget about the sine. Just say 5x times 5x over x squared. That will give you 5x squared on x squared, which is equal to 5x times 5x is 25x squared divided by x squared, which is 25. This limit here, you can do it in 2 ways like that for very small angles. You know how sine behaves very small angles. But for very small angles, cosine is 8 times by 1. This is just the same thing here now. It's approximately equal to 1 over x. As x tends to 0, this thing tends to infinity. Forget about the sine, forget about the tan. It's just x over x squared, which is equal to 1 over x. As x tends to 0 is infinity. The same thing here as x tends to 0. But as x tends to 0, we are going to have 0 over 0. So we can actually use L'Hopital's or other rules, other ways. So this one can be the same as sine x on x. So this will just give us x as x tends to 0. Can you see x squared? Just say, forget about the sign. X squared divided by x is x, right?
Yes, sir.
What's the value of x as x tends to 0? The answer is 0 now. And this is the 0 down here. These are shortcuts. Very important shortcuts. Look at all of this big solving. I've just told you the answer without solving. You just have to open your mathematics left eye and see. So we can equally look at all of these ones. The same principles. Can apply them. Alright, there are so many of them. Alright, any questions? I think this is where we come to the end of the tutorials. Yes, any questions? This one is found in chapter 2, or is it chapter 7? Chapter 7a, b, a and b. Just take highest degree divided by highest degree. The answer is 2 over 6. Something like that. 2 over 6 divided by 3 is 1 over 3. See, this is the answer here. But look at all of the big working. Don't follow this procedure for this one because you already know how to do this one. This is a rational function. Just take highest degree 2x squared divided by highest degree 6x squared. The answer comes out directly 2/6, which is equal to 1/3. This is the answer down here. So you see how explanations can frighten people? But look at the
So
L'Hopital's
that
way
one
of doing it.
again.
You differentiate, differentiate, and differentiate again. No, no, no. Just take highest divided by highest, as I showed you in chapter 7a, the A part of this chapter, and you have the answer directly. No stress. Yeah, well, this one we can equally work it out. It's very clear here. Please look at these two also. As x tends to negative infinity, so we'll just have negative infinity over e to negative infinity. And we can arrange, we can transform it to this form. We differentiate by applying L'Hopital's rule. We have x over e to the power minus x. Differentiate numerator, differentiate denominator. This is what we are going to have. Minus e to the power minus x. And as x tends to infinity, we have 1 over minus e to the power minus minus infinity, which is plus infinity. The answer is still going to be equal to 0. Don't be stressed with the solving. So these are, we have already looked at all of these ones. We have already looked at all of them. In this particular lesson, I explained them step by step. I also explained these ones. So this brings us the end of this lesson. Hope you can go to YouTube and share these videos with your friends too, and so on, and all other people. Any questions for me today?
No.
All right, if you have other
Yes,
questions, you can leave
I have a
in the
small
WhatsApp group.
question.
Yes.
They, if they give you a question like 15 divided by root 3, how will you solve it?
Root 3 divided by root 3.
15 divided by root 3.
15 divided by root 3 as x tends to what value?
So that's just the question.
15 divided by root 3. Yeah, you can simplify. Okay, let me see how I can do this. That's on cells, right?
Yes, sir.
Well, 15 divided by root 3. How do they want the answer to be? In the form of a third or
So
what?
that's how they just send it. I tried solving, but I don't know whether the answer is correct.
15 divided by root 3 is the same as you multiply numerator and denominator by root 3 now. So you have
Yes, sir.
15 root 3 over root 3 times root 3. Root 3 times root 3. But root 3 times root 3 is 3, right?
3.
Yeah, so we have 15 root 3 divided by 3. And 3 here 1, 3 here 5 times. So the answer is equal to 5 root 3 now.
So thank you.
Alright, you're welcome. Alright, so I think we'll have class tomorrow at 8 o'clock. The video will be uploaded before the class time, so you can watch the video before it is 8 o'clock tomorrow. And the 2 other videos that we're missing have been uploaded too. I've just been informed now that the other videos, lessons 2 on further maths, are on their way. Alright, thank you so much, and happy Sunday.
Thank you, sir.
You're welcome. Okay.